Transition state theory, which used to be called activated complex theory, is this idea that if we look at a single step in a reaction, and that has rate constant K, that K is a function of the properties of the transition state and the reactants. Okay, if K is for this forward reaction, so we're looking at energy and reaction progress, the reaction coordinate, that the rate in the forward direction is a function of the properties of the stuff you start with and of the transition state. If we could just work that out, we should be able to come up with a number for K. That's the idea of transition state theory. So the mechanism for transition state theory is that you've got reactants, and they go in a step, which we'll call substep K, to form the transition state. Let's just call this, we'll call this K for forming the transition state. And that the transition state can fall apart to form reactants. And remember, this is not even a complete mechanistic step. This is a sub-step, because a transition step can then go on, we'll call this K double dagger, to not decay backwards, but to go forwards to products. So this is the overall transition state theory idea for modeling a single mechanistic step, that first we have to form the transition state, and then it goes on to form products. And this formalism allows us to come up with K for this reaction. So what we're going to do is look at a couple of case studies, because we'll look at cases where we have this first step might be unimolecular or bimolecular, it might be gas phase, it might be solution phase, and the details of the derivation are a little bit different for each of these cases, but the overall theme is the same. So let's look at bimolecular solution phase first. So in this case, we're going to have a molecule of A and a molecule of B forming the transition state, and that goes on to form product. And we know if we look at this second sub-step, we can say the rate, which is the rate of product production, is just going to be concentration of transition state times that rate constant K double dagger. So we need to know this. We also need to know the concentration of transition state. So let's take each of these pieces in turn. Let's do concentration of transition state first. Well, we can look at this part and say, oh, we've got this quasi-equilibrium going on here. And so let's write a sort of transition state equilibrium constant for that forming the transition state. We can see it's going to be concentration of transition state divided by 1 molar, if we're going to use a 1 molar standard state, divided by the concentration of A over 1 molar times the concentration of B over 1 molar. And we can see these units of 1 molar cancel. We're left with 1 standard concentration there. If we wanted to, we could abbreviate this with just a C standard, saying the standard concentration. Note that we're not using activity coefficients here. So what we're doing by omitting activity coefficients is to imply that this is an ideal solution. If we were working with something where we knew this weren't true, if let's say that we were working with an ionic solution with electrolyte reactants, we'd want to plug in activity coefficients too. All right, so we've got K double dagger is equal to transition state concentration times the standard concentration all over A times B. So if we were working in dilute aqueous solution, then the standard concentrations in 1 molal. If 1 molal is standard concentration, but if we're working in dilute aqueous solution, we always approximate that with molarity. Okay, So we can solve this for concentration of transition state. So concentration of transition state is going to be that equilibrium constant times A times B divided by the standard concentration. So we can plug that in over here. All we have to do is find K double dagger first. So now we have to find small k double dagger, the rate of transmission from the transition state until products. Well, K is going to be equal to two things. Something called the transmission coefficient, which is a small kappa, and nu, which is the vibrational frequency along the reaction coordinates. So let's annotate those. So you can imagine that molecules vibrate in a bunch of different normal modes, but one of those normal modes could correspond to the bond breaking and bond making of the transition state. And this is called the transmission coefficient. And it just corresponds to does every single vibration of along the reaction coordinate result in bond breakage. So if you have to vibrate several times along the reaction coordinate before the bonds snap and you go on to products, K would be less than 1. On the other hand, if every vibration that the transition state made along the reaction coordinate resulted in product, then K would be equal to 1. So we're going to assume that kappa is approximately equal to 1. Now, how do we find the vibration frequency along the reaction coordinate? Well, according to statistical mechanics, that vibrational frequency should be approximately equal to the thermal energy over Planck's constant. And if it were basically this tells us something about the bond strength. If the bond strength along the vibration coordinate were very strong, we'd have a higher vibrational frequency, but we also wouldn't be able to break the bond because this thermal energy has to be comparable to the bond strength, or we wouldn't actually break the bond. So we're just going to pull that result in from statistical mechanics, and that gives us that K double dagger is approximately 1 times this expression. So we have the thermal energy divided by Planck's constant. And it's been a while since you've seen that, so let's put that in 6.62 times 10 to the minus 34 joule seconds. Okay, so now we have this expression. If we wanted to, we could actually calculate this number for room temperature. What is this for room temperature? We plug all those numbers in, we get that this should be approximately equal to 6 times 10 to the 12th reciprocal seconds. So another way of saying this is that the vibrational time for vibration along the reaction coordinate is going to be less than a picosecond. So our transition state has a very fleeting existence because it's vibrating with this frequency, and we're saying that basically it completes only one vibration and then snaps apart into products. So less than a picosecond lifetime for our transition state. Now once we have this, we can put the pieces together. We said the rate was going to be equal to the concentration of A times the concentration of B times the equilibrium constant for forming transition state divided by the standard concentration, and now we have to multiply by our rate constant for the transition state forming products. So that was KT over H. So you put all the pieces together here. If this is the rate, and this is a bimolecular reaction, we know that we could also say it's going to be K times concentration of A times B. Because let's not lose sight of the reaction, right? It was A plus B in a single step forming products. And so if it's a single step and it's bimolecular, then it's going to be second order overall over here. So that means we can identify this entire expression as K. So we have an equation for the rate constant. The rate constant that we would determine experimentally for this one-step reaction would be KT over Planck's constant times the equilibrium constant for transition state formation divided by the standard concentration. This equation is one form of the Eyring equation. So the Eyring equation is the equation for the rate constant given in terms of properties of that transition state and the reactants. Now notice, we haven't come up with an equation yet, but we know it has to be that the equilibrium constant for forming transition state has to be a function of properties of transition state as compared to those of the reactants. So let's go on and do this a little bit further. So for a solution phase reaction, it's bimolecular. We saw that the rate constant is given by this expression, but we need to know what is this K double dagger here? What's an equilibrium constant? And for any equilibrium constant, we can say that delta G standard, so this time it's a delta G standard double dagger, is negative RT log of that equilibrium constant. And this is not the difference between products and reactants. This is the difference between the transition state and the reactants, right? Because this is a K not for forming products, but for forming transition state. So we can say K double dagger is equal to E to the negative delta G double dagger over RT. And we can put this in this expression and get a new expression for the rate constant. It's KT over HC, where C is the standard concentration, times E to the negative delta G double dagger over RT. So now we can see, the Gibbs energy of the transition state and the reactants, that difference is going to determine this size of this reaction. And so we can actually get quantitative about the relationship between a rate constant of a reaction and the Gibbs energies of transition state and reactants.